Pseudonymization is one of those privacy words that can sound comforting while still leaving plenty of risk on the table if it is done casually. The basic idea is that you replace direct identifiers, like a name or email address, with a substitute value so the data is less obviously tied to a person. That substitute might be a random token, a generated ID, or some other label that stands in for the person in your systems. What makes this topic tricky is that pseudonymization is not the same as anonymization, and it is not a guarantee that the person cannot be identified. If the system still has a way to reverse the substitution, or if the pseudonym can be linked across many contexts, then you can still end up with a detailed profile. The real question is whether your controls turn pseudonymization into meaningful protection, or whether it becomes a thin layer of paint over a system that still behaves like it is tracking individuals everywhere. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A beginner-friendly way to frame pseudonymization is to think of it as separating identity from activity. Identity is the information that points to a specific person, while activity is what that person did, like actions, events, or transactions. Pseudonymization tries to keep activity usable for legitimate purposes while making it harder for most systems and most people to immediately connect that activity back to a named individual. This can reduce exposure when data is shared internally, when datasets are used for analytics, or when systems are breached. However, if identity and activity are still stored side by side, or if the mapping between them is easy to access, the protection is weak. Controls are what make the separation real, and controls are what determine whether pseudonymization changes the practical risk. The biggest mindset shift is that the pseudonym itself is not the protection, the way you manage it is. It helps to clearly distinguish pseudonymization from anonymization, because confusion here leads to poor decisions. Anonymization aims to make it extremely difficult to identify individuals from the data, even with other information, while pseudonymization keeps a link to the person somewhere so the data can still be related back when needed. That link is often called a mapping or a key, and it is the most sensitive part of a pseudonymized design. If someone gets the mapping, pseudonymized data can become identifiable again quickly. Even without the mapping, a pseudonym can still enable linkability, meaning you can track the same person over time within the dataset. That might be acceptable for certain purposes, but it is still a privacy capability that needs justification. A defensible design is honest about this and does not pretend pseudonymization makes data risk-free. The first practical control that actually matters is deciding what the pseudonym is allowed to do. If you reuse the same pseudonym across many products, channels, and datasets, you are effectively building a universal tracker, just with a different label. A stronger approach is scoping, where pseudonyms are limited to a specific context or purpose. For example, a pseudonym used for fraud detection might be different from a pseudonym used for product analytics, and neither one should automatically join to a customer support view. Scoping reduces blast radius because even if one pseudonym is compromised or misused, it cannot easily connect everything else. It also reduces temptation because cross-context joining becomes harder and therefore more deliberate. Scoping is one of the simplest ways to make pseudonymization feel like real protection rather than just a new identifier that follows someone everywhere. The second major control is protecting the mapping, because the mapping is where the re-identification capability lives. A common failure is storing the mapping in the same environment as the pseudonymized data, accessible to many systems and many people. That design makes pseudonymization cosmetic, because anyone who can query one system can often query the other. A stronger pattern is to store mappings in a dedicated, tightly controlled service that exposes only limited functions, like resolving a pseudonym to an identity when a specific business need exists. This service should be designed so that most workloads never need to call it. When the mapping is isolated, you can apply stricter access control, stronger monitoring, and stricter retention rules to the most sensitive component. The protective power of pseudonymization rises sharply when mapping access becomes rare, reviewable, and difficult to misuse. A third control is choosing the right technique for creating pseudonyms, because weak techniques can be reversed or guessed. The safest approach is typically to use randomly generated tokens that do not contain meaning and cannot be derived from the original identity. Beginners sometimes see hashed emails used as pseudonyms, but hashes can be vulnerable when the input space is predictable, like common email formats or known lists of addresses. If an attacker can guess the original values and compute hashes, the pseudonyms can be reversed through matching. That means using a simple hash of an identifier is often not strong pseudonymization. Even when more complex methods are used, you still need to treat the pseudonym as sensitive because it can enable tracking within the dataset. Strong pseudonymization starts with a pseudonym that is hard to guess and hard to reverse, then relies on controls to limit linkability and resolution. Rotation is another control that often separates serious pseudonymization from superficial pseudonymization. Rotation means changing pseudonyms over time or across events, so long-term tracking becomes harder. If a pseudonym stays stable forever, it becomes a persistent hook that can be used to build a long-term behavioral profile, even if nobody knows the person's name. Rotating pseudonyms can limit that by shortening the time window of linkability. The trade-off is that rotation can make certain analyses harder because analysts lose long-range continuity. Privacy engineering treats that as a design decision rather than an accident. You choose the smallest continuity window that still supports the legitimate purpose. When someone challenges your approach, being able to explain why the pseudonym is stable or why it rotates is a sign you've thought about the privacy impact, not just the convenience. Access control is where pseudonymization either becomes meaningful or becomes a false comfort. Even if the mapping is protected, the pseudonymized dataset itself can still reveal sensitive information, and broad access can still enable misuse. Most teams do not need row-level data tied to stable pseudonyms. They need aggregated metrics, trends, and segments that do not allow individual tracking. A defensible design provides different views for different roles, so most users see only summaries, while a small group with a defined purpose can access pseudonymized rows. This is also where auditing matters, because pseudonymized data is still about people, and you should be able to detect unusual querying or bulk extraction. If a system treats pseudonymized data like it is harmless, it tends to become widely shared, copied, and retained, which undermines the entire goal. Controls have to reflect the reality that pseudonymization reduces risk but does not eliminate it. A subtle but important control is limiting which attributes travel with the pseudonym, because the surrounding fields can re-identify a person even without the mapping. If you store a pseudonym alongside precise location, precise timestamps, a rare job title, or unique behavioral sequences, an attacker may identify the person by uniqueness alone. This is why pseudonymization often needs to be paired with minimization and generalization, especially for quasi-identifiers. The pseudonym hides the obvious label, but the data can still tell a distinctive story. A practical approach is to review the dataset as if you were trying to identify someone you already know, using only the attributes present. If you can pick them out easily, your pseudonymization is not providing much real protection, regardless of how well the mapping is guarded. Pseudonymization also needs strong controls at the boundaries where data moves, because that is where identifiers often leak back in. For example, an analytics pipeline might be fed pseudonymized events, but then a debugging log might include the original user ID for convenience, creating a shadow mapping outside the controlled service. Support tools might show pseudonyms, but also allow free text notes that include names or emails copied from other systems. Data exports might include both pseudonyms and direct identifiers in the same file because someone merged tables for a report. These boundary leaks are common because people solve immediate problems and do not always see the long-term consequences. A privacy-aware approach anticipates them by restricting exports, controlling logging, and designing tools so staff can do their jobs without needing to paste direct identifiers into uncontrolled places. Pseudonymization only protects if the rest of the system stops reintroducing identity through side channels. Another area where pseudonymization controls often fail is in joining behavior, because data warehouses make joins easy. If multiple datasets share the same pseudonym, analysts can combine them into a detailed profile even without knowing the person's name. That might still be too much power depending on the purpose and the sensitivity of the data. This is why scoping and zoning matter, and why some pseudonyms should be intentionally non-joinable across domains. When joins are necessary, they should be purposeful and constrained, not the default. A helpful practice is to treat cross-domain joins as high-risk operations that require justification, limited access, and careful output controls. If anyone can join any table by a stable pseudonym, you have recreated the core risk of aggregation, just without the obvious identifiers, and that is usually not a strong privacy outcome. Retention is also part of making pseudonymization actually protective, because long retention turns stable pseudonyms into long-term dossiers. If you keep pseudonymized data forever, you may not store names, but you still store behavioral history that can be sensitive and that can sometimes be linked back later. A stronger approach is to shorten retention for row-level pseudonymized data and keep longer-lived aggregates that do not preserve individual continuity. You can also set different retention windows for different purposes, so high-risk domains expire faster. Importantly, the mapping often needs even stricter retention because keeping mappings indefinitely preserves the ability to re-identify long after the original purpose has passed. When a system deletes the activity records but keeps mappings forever, it can still become a re-identification tool for any new dataset that later appears. Deleting mappings on purpose is one of the most powerful ways to make pseudonymization a real safety control. Defensibility is the final test. Can you explain your pseudonymization design in a way that a skeptical reviewer would accept as thoughtful and disciplined? You should be able to state what purpose the pseudonym supports, how it is scoped, who can access the pseudonymized dataset, and who can resolve it to identity. You should be able to describe how the mapping is protected, how access is audited, and how retention limits reduce long-term tracking. You should also be able to explain what risks remain, such as residual linkability within a limited window, and what additional controls reduce those risks, like minimization of quasi-identifiers. Defensibility is not achieved by using fancy words or by claiming the data is anonymous when it is not. It is achieved by showing that your system structure makes misuse difficult and makes privacy boundaries real in daily operation. When pseudonymization controls actually protect, they work together like a set of locks rather than a single trick. The pseudonym is scoped so it cannot become a universal tracker, and it is created in a way that resists guessing and reversal. The mapping is isolated, tightly controlled, and rarely used, so re-identification is an exceptional event with oversight, not a normal convenience. Access to pseudonymized rows is limited. Most analysis happens on safer aggregated outputs, and the data is designed to avoid uniqueness that can re-identify people indirectly. Boundaries prevent identity from leaking back in through logs, exports, and casual merges, and retention rules ensure the system does not accumulate long-term dossiers. Pseudonymization is not a guarantee, but when you design it with these controls, it becomes a meaningful privacy engineering tool that reduces harm in realistic ways rather than just changing labels.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.